All right. So more on polynomials here. There's your formal definition of possible rational zeros. I know we've already discussed them, but there's the formal definition if you do need to reference it. So for example, when it says write a polynomial in factored and standard forms with the following zeros. So when I give you these zeros, these are all real number zeros. So when they're all real numbers, or all rational, I guess I should say rational numbers, these are the only ones that exist. So we're basically given the zeros and we're going to work our way backwards to create the polynomial itself. So I have zeros of x equals 3, x equals -2, and x equals 1. First thing we want to do is move each zero back to the same side as x, so kind of like unsolving. So we'd have x minus 3 equals 0, we would add 2, x plus 2 is 0, and then subtract 1, x minus 1 is 0. So doing this process backwards, we're going from the zeros to each factor set equal to 0. So now we're going to break that part even further and just go back to factored form. So the factored form, let's see, I'm going to scooch this back over here so it's all over there. It says a polynomial, so you can call it whatever you'd like. I'm going to go with p of x since it's a polynomial. The factored form of our polynomial would be x minus 3 times x plus 2 times x minus 1. So here's factored form, done with the factored form. For standard form, so it does say both here, for standard form, we would simply just expand and combine all like terms here. So I'm going to do standard next to it. A little separation. All right, so it doesn't matter which two you multiply out first. I'm going to choose these first two since they're side by side. So you're running through FOIL. So first outside, inside, last. X times x is x squared. Outside is going to give us 2x, and inside is going to give us -3x. 2 plus -3 is -1. And then last, -3 times 2 is -6. And I'm going to drop my x minus 1 down. Right, now we want to multiply these two together, so everything in that first set of parentheses gets multiplied by the x minus 1. So we're going to get x squared times x cubed, and then x squared times the -1, negative x squared. Then I move to the middle term. Negative x also gets multiplied by both of those. Negative x times x, negative x squared. Negative x times -1, positive x. And then I go to my -6. -6 times x, -6x. -6 times -1, positive 6. Then we combine what we can. So x cubed is all by itself. Then we have -x squared and another -x squared. So it's going to be -2x squared. 1x minus 6x is going to be -5x. And then our plus 6. So here is our standard form, which is just everything all multiplied out as much as possible. So you could write it both ways, just dependent on the directions. All right, so again, this applies when the polynomials have rational zeros. Now, when we bring in irrational or complex zeros, they must come in a pair, okay? So it's called a conjugate pair. All right, so this time it says if a polynomial with degree 4 has known zeros of -square root of 2 and -3 plus the square root of 5i, what must be the remaining zeros? So anything involving a square root or an I, because technically an I is a square root as well, has to come in what's called a conjugate pair. So there's your definition up here. So it's saying if, we're talking about complex zeros, if a plus zi is a root, then its conjugate, a minus bi, must also be a root. So we'll look at that conjugate complex one first. So if -3 plus the square root of 5i is a 0, -3 minus the square root of 5 times I must also be a 0. So this is also a 0, or root, interchangeable. Then the next one is your irrational roots. So it says if a plus c times the square root of b is a 0, its conjugate, a minus c times the square root of b, must also be a 0. So they need to come in a conjugate pair as well. The only ones that do not come in conjugate pairs are rational zeros like what we dealt with in example 1. So if we look at the other one, the negative square root of 2, if negative square root of 2 is a 0, then positive root 2 is also a 0 or root. So those are the other two that we're missing. Actually, let me scooch this up so that it does display. All right, example 3. Find all zeros of the polynomial function f given that x equals 1 is a 0. So this one's been adjusted a little bit from the last time. So the difference now is with this one, we know we have a 0. We know that x equals 1 is a 0. So what that does is that saves us from having to play the guessing game through synthetic division. So if x equals 1 is a 0, I want to remove it using synthetic division. So x equals 1 is a known 0. Therefore, we're going to get it out of the way and we'll work with what's left. So I'm going to pull my coefficients in order. X cubed, x squared, x, and my constant. So another thing I suggest you do is it says that this is a 0. If it is a known 0, your remainder has to be 0. So I'm going to go ahead and fill that 0 in. If I don't get 0, that means I've got an issue with my algebra and I need to go relook at it. All right, first one, all the way straight down. And then we're multiplying. 1 times 1 is 1, column addition, 0. Back to the one at the top left. 1 times 0 is 0, column addition, 1. 1 times 1 is 1, column addition, 0. So it does work. If you do not get 0, you need to go look at your algebra again. All right, so what this is we've removed the known 0, which means what we have left to solve is we drop the degree by 1, x squared plus 0x. There's no reason to list the plus 0x, so I'm going to leave it off. Plus 1 equals 0. This is the remaining polynomial. So it was a degree 3. We just took it down to a degree 2. So rather than trying the guessing game, because now we're bringing in the irrational and complex roots, the goal is to get it down to a quadratic, which is an x squared. Once it's down to an x squared, we can try factoring, quadratic formula, or completing the square, whichever you prefer. Factoring will not always work, so I would recommend one of the other two. So we're on to step 2. I'll zoom out where you can see step 2. Solve the quadratic equation using one of your methods. All right, x squared plus 1 is what we have left to solve. Because it's just an x squared, I'm going to use the square root property because it's pretty quick. This only works when you have just an x squared. If you have the x squared and the x, you cannot use this idea. So I've got x squared equals -1. To remove the exponent, we square root both sides of our equation, remembering to put in a plus or minus. So we get x equals positive or negative. I have a negative under a square root. Remember that negative always comes out of the square root as an I. So I would bring that I out. That takes the negative off the number underneath. And I'm kind of out of room this way, so we'll just go sideways. So that means x equals plus or minus, and the square root of 1 is just 1, so plus or minus I. So those are going to be my remaining zeros that I just found. So then last thing is to remember to list all of the zeros, including the one you took out with synthetic division. So our zeros are x equals the one we removed at the very, very beginning. X equals 1, even though it was given, it is still a 0. And then make sure you get a comma in here, plus or minus I. So there were 3 zeros. All right, next one. Find all zeros of the polynomial f given that x equals 2i is a 0. So first thing we want to do is remove the known 0 with synthetic division. So another red flag. This is a complex 0. It's got an I. So if x equals 2i is a 0, x equals -2i is also a 0. So right off the bat, I know 2 zeros. So what we want to do is we want to take them out one at a time using synthetic division. Technically, it doesn't matter which one you take out first. I'm going to take out the positive 2i. All right, set up. Now, the synthetic division with an I, the first round can be a little bit painful. Be very careful with your algebra. Pull your coefficients. So I've got a 1 for x to the 4th. X to the 3rd has nothing, so 0. X squared also has nothing. X has nothing. And finally, the negative 16. It's very, very important you get those zeros in there or you will get the wrong answer. All right, we know the remainder has to be 0, so I'm going to go ahead and fill it out. Notice I left a lot of room in here. All right, straight down. 1. Remember, we are multiplying. I'm going to show work for these. 1 times 2i is 2i. Column addition, 0 plus 2i is 2i. Okay, now we're going to go back to that 2i in the top left. So what we're doing here is 2i times 2i. So it's 2 times 2, 4. I times I squared. And then I'm going to put a note up here at the top. But you got to remember, it's been a while. I squared is negative 1. We do not leave anything simplified with an I squared. We always plug in a negative 1 for it, which in result is going to change the sign of that 4 because we're going to get 4 times negative 1. So it becomes negative 4. And then we're doing column addition with the simplified form of that. So 0 plus negative 4 is negative 4. I'm coming back to that 2i in the top left. So now we've got our negative 4 times 2i. Negative 4 times 2 is going to be negative 8. And there's only one I this time. Column addition straight down. 0 plus negative 8i is negative 8i. I'm back up here with our 2i. So now we have 2i times negative 8i. I'm going to put these in parentheses because it looks a little bit better. All right, 2 times negative 8 is negative 16. I times I squared. I squared gets replaced with negative 1, which changes the sign of that to a positive 16. And then negative 16 plus 16 is 0. And then you can breathe because you got a remainder of 0. If you do not get a remainder of 0, you have an algebra error somewhere, and we need to get that fixed. All right, so notice the resulting coefficients are very, very ugly. The reason they're ugly is because remember, anything with an I or a square root comes in a conjugate pair. So before I do anything, I am immediately going to go ahead and take out the other 0, negative 2i. So I'm just going to extend this down. Make sure you change the sign. Now we are going to take out negative 2i. Another recommendation, remember each time you do synthetic, you're going to lose a column. So I'm going to go cross this off because I am done with that column. So now my remainder is going to go here. All right, same process, straight down. 1. Negative 2i, I'm going to write them. 1 times negative 2i is negative 2i. Column addition straight down is 0. Then we have 0 times negative 2i, which is 0. Column addition, negative 4. And then we have negative 4 times negative 2i. Negative times negative, positive. 8i. Column addition, 0. So see, one round's a little bit rough with multiplying on the i's, but it should all fix itself at the next step. All right, we got our remainder of 0. So that means once we have now taken out those two zeros. So each time you take out a 0, you take it down a degree. So when we took out the 2i, right here we were looking at an x cubed. Now that we have taken out a second root, the degree drops by 2. So it was an x to the 4 here. It is now going to be an x squared. So what's left is x squared plus 0x, which is kind of pointless in writing, minus 4 equals 0. So this is the quadratic equation that we have left to solve. So now that we've removed the known zeros, we're going to go solve what's left. So x squared, I'm going to drop the 0 in the middle. All right, with this one, we could use the same idea as before, the square root property, or you could choose factoring because it does work. It doesn't matter. I'm going to choose factoring this time just so you've got a different example. If it doesn't factor, complete the square quadratic formula, or you could square root it if it's just x squared. So we split it x and x, split up the 4. It's 2 and 2. Anytime the x is missing, it's the same number, just opposite signs. So then we would have x plus 2 equals 0, and we would have x minus 2 equals 0. And I'm scooching it over, I'm out of room. I'm gonna go up here. And just so all the work's nice and neat. Well, you know what, I think I can fit them in. So we would subtract 2, so x is negative 2. Over here we would add 2, so x is positive 2. Same answers as if you would have square rooted both sides. Finally, don't forget to list all of your zeros. So our zeros are the 2 we just found. Since they're both the same number, I'm just going to put a plus minus in front of the 2. And the ones we took out, so we took out a 2i and we took out a negative 2i. So plus or minus 2i as well. So there are 4 zeros here. And it's fine to list them like this. If you prefer to list them separately, you can. Negative 2, comma 2, 2i, comma, negative 2i. Either way works. So list it whichever way you prefer. Come on, rectangle, please. All right. Example 5. Find all zeros of the polynomial, then write f of x as a product of linear factors. So 2 new things. 1, we're not given a 0. So that means we either have to go back to the guessing game like we did last section, or maybe we'll get lucky and it'll factor by grouping. And then write it as a linear product of linear factors. So we'll worry about that product in just a minute. So find all zeros. So that means we're setting this equal to 0. So I've got 2 choices. I can try to factor it, or I can play the guessing game. So let's see if this is going to factor. Maybe we'll get lucky. So remember, factor by grouping goes along a plus sign. Never stick a minus sign in the middle because that changes the sign of numbers. All right, so take out what's common. The first group has an x squared in common. Just going to drop the exponent by 1, so it's down to an x. We took the whole x squared out. Remember, when you take out the whole, either a plus or a minus 1 holds its place. So the goal is to make that back set of parentheses look just like it. So if I've got to turn negative 3x into an x, I'm going to take out the negative 3. That leaves us with x. I took out a negative 3 from the 3, so think division. 3 divided by negative 3 is going to be a negative 1. And if we look, the sets of parentheses are the same, so this is factor by grouping works. No reason to go back to synthetic division and play the guessing game. Now you could if you wanted to. I don't have the patience to guess at zeros. I'd rather just find them right away. So we're going to group them. We slide the x squared and the minus 3 together. So that's from what we took out on the front of each. Actually, let's do the box. So the x squared here. Let's fill that in. And the minus 3 slide together to make one factor. Oh, come on, draw a box. So one bubble. And then the other bubble that's the same gets written one time. All right. So at this point, remember it's factored. This one here technically does not factor further like we're used to, so I'm just going to hold off on factoring. I'm going to go ahead and set each to 0 and continue solving. So here we would add 3. Square root both sides. Do not forget that plus or minus. So x equals, it's not negative, so no I. Plus or minus the square root of 3 does not reduce, nor is it pretty, so we don't touch it. And then over here we would add 1 and get x equals 1. So here are the 3 zeros. So these are our zeros. Actually, we'll just write the word zeros next to them. That looks better. All right, so find the zeros. Done. 2, write it as a product of linear factors. So a product of linear factors is like taking your zeros and working backwards. So for the product, rather than leave those zeros as plus or minus square root of 3, I want to separate them. So x equals the square root of 3, x equals the negative square root of 3, and then the x equals 1. So it's the same idea as what we did in the first example. It's just we have ugly irrational zeros this time. So we're going to move each back to the same side as x. So that would be like subtracting the square root of 3 from both sides. Same thing with the second one. We're going to add the square root of 3 here. And then for the 1, we would subtract the 1. So each of these is your linear factor. So then I've got the factor x minus the square root of 3, the factor x plus the square root of 3, and the factor x minus 1. So this is the linear factorization of f. And if you can catch that x squared minus 3 factors to x plus root 3 and x minus root 3, you can use that. But I do think it's easier to just go all the way to the roots and then write the factored form. So here is your, you know what, I'm going to underline this part here so we know that's what the pink is for. So that's what the pink works for. All right, next one. Find all the zeros of f and then write f as a product of linear factors. So we're doing the exact same thing we just did on the one we just finished. All right, so notice again, we're not given any zeros. So that means either we can get lucky and it factors by grouping, or we actually have to go play the guessing game like we did in the last section. So let's see. All right, if we try the grouping. So right away, I can look at this and tell it's not going to work. If you try, you take out the x squared. It's going to leave you with an x and a minus 7. And when I'm looking at the back, 9, there is absolutely no way I can turn 9 into 7. So factor by grouping's out. Bring on the guessing game. So, all right, I'm going to list the possible rational zeros first to kind of give me a starting point for this guessing game. Rational. All right, so your possible rational zeros, recall, factors of the constant divided by factors of the leading coefficient. So if there are rational zeros, they have to be factors of 9 divided by, because that's our constant, factors of, I think it was 1. Is it leading coefficient? Yeah, 1. So factors of 9. Since the denominator is 1, there's no reason to list it. So plus or minus numbers that multiply to 9 are 1, positive or negative, positive or negative 3, and positive or negative 9. So we get to go play our guessing game. So we've got our polynomial x cubed minus 7 x squared plus 9 x plus 9. So again, it's kind of luck of the draw as to whether you figure out what this 0 is. So I don't know. Let's see. Let's try positive 1. See if it works. So I'm going to attempt to take out, I said positive 1. 1 with synthetic division. All right, so coefficients 1, negative 7, 9, and 9. So remember, we have to get a remainder of 0 for this to work. So first one straight down. 1 times 1 is 1. Negative 7 plus 1 is negative 6. 1 times negative 6 is negative 6. 9 minus 6 is 3. Ugh. 1 times 3 is 3. And all that matters is it's not 0. It's 12, but it's not 0, so guess what? It doesn't work. So, like I said, it's kind of your call as to what you go to next, because basically this round of synthetic division was completely pointless. I don't want to erase it. I do want to leave it up here just so you know we're totally ignoring it because it didn't work. So we're just going to put a note, ignore. Because that is not a 0. We can't do anything unless we get a 0. So let's go try something else. I don't know. I'm going to change it up. I'm going to go to 3. This guessing game is not fun. All right, so we're pulling the exact same coefficients because it did not work. 1, negative 7, 9, and 9. Round 2. Drop the 1. 1 times 3 is 3. Negative 7 plus 3 is negative 4. 3 times negative 4 is negative 12. 9 plus a negative 12 is negative 3. 3 times negative 3, oh good, negative 9, bar's not long enough. 0. Perfect, so that one worked. All right, so because we're having to guess, I'm gonna put a little note here. Note, since remainder equals 0, x equals 3 is a root. So I have one of my roots. So what that means is I can actually use these numbers that we just got right here to reduce it down. So what's left to solve using these 3 numbers? Remember, drop the degree by 1. The original degree was 3, so we're down to an x squared. So what's left is x squared minus 4x minus 3 equals 0. Once it's down to a quadratic, you can try to factor, but it doesn't always work. Or you can complete the square or use the quadratic formula. Completing the square and quadratic formula will always work. Okay, so I'm going to go with quadratic formula. A lot of you like that one, so that's what I'm going to stick with. But again, if you use completing the square, you will get the exact same answers in the end. It does not factor, so factoring's out this time. Quadratic formula. So x equals, I'm going to get my template set up. Go back to blue. So a negative, actually, you know what? I'll write the formula out for you. Negative b plus or minus b squared minus 4ac with that chunk under a square root. Whole thing gets divided by 2 times a. In case you've forgotten it, there it is, so you can reference it. All right, so I want to get my template set up first. So x equals, I've got a negative and then a bubble because I'm plugging in for b, plus or minus another bubble for b squared minus 4, a bubble for a, and a bubble for c, and that whole back part is under a long square root. Extra long division bar, 2, and then a bubble for a. All right, a is in front of x squared, so 1. B is in front of x, negative 4, and c is the constant, negative 3. So plugging in b, and then it's a, which is 1, and then c, negative 3, all over 2a, 1. All right, x equals, double negative makes a positive 4, plus or minus, negative 4 quantity squared, careful there, that is 16. And then we have, I'm going to change this to plus a negative. So negative 4 times 1 is negative 4. Negative 4 times negative 3 is going to be 12. Don't forget your square root. All over 2 times 1 is 2. All right, then we have 4 plus or minus 16 plus 12 is 28. 10, 28, yep. All over 2. All right, at this point, then you've got to look and decide what's next. So there's no negative, so that means there is no I to worry about. 28 does not have a pretty square root, so we cannot keep going. That's because it wasn't factorable. However, 28 does reduce. So remember, you're looking for numbers that come out of 28 that are perfect squares. So you're looking for 28 to be divisible by either one of the following: 4, 9, 16, 25. You don't go bigger than 28, so those are the only 4. 28 is divisible by 4. So what we would do here, let me draw an arrow because I'm running out of room. I'm going to go this way. All right, I'm going to copy this for you so we can see that's the exact same step right there. All right, so we said 28 was divisible by 4. 28 is 7 times 4, so I'm just going to rewrite 28 as the product of 4 times 7. And then the square root of 4 is nice and pretty, so that means we can actually square root it and bring it out. The square root of 4 is 2. So the 2 comes out. 7 does not have a nice root, so it stays underneath. And then all over 2. And then here's where you want to be super, super careful. You've done a ton of work. You hate to mess up at the last step. So then you're looking at the V shape. I am trying to decide if I can reduce both of those. I said V shape and then I drew a U. So I am looking for 2 to divide on both of these. So the 4 gets the 2, and then the 2 out front gets it. So if you want to think about this, it's like you're splitting it as 4 over 2 plus or minus 2 root 7 over 2. Each one is going to get that division by 2. And I did not go up high enough, so I'm going to scooch you a little bit. There we go. I'm also going to turn that arrow that way. And then 4 over 2 is 2 plus or minus these 2's divide out, which leaves us with just the square root of 7. You have to simplify completely here. All right, so we have the last roots. Yes. All right, so all zeros listed together. And you know what? I'm going to keep on scooching up because I just can't seem to leave myself enough room to write everything. All right, so our zeros. Are x equals 2 plus n minus the square root of 7, the 2 that we just found, and the 1 that we took out with synthetic division, the 3. The 1, do not accidentally list that 1 that we tried first, because remember, we ignored that round of synthetic division because it did not work. So everything right here in this box, it's kind of pointless because we didn't guess right, so it's totally ignored. It has nothing to do with one of those answers. So we have our zeros. All right, your linear factors. So we'll do this one in pink like the last one. So I'll just write product. So it's going to be the same as the last time. It's just going to look a little weird. Start with each separately. So no plus or minuses we want involved. I want every zero listed on its own. So 2 plus the square root of 7. Then we have 2 minus the square root of 7. And finally 3. So we want to move these over, okay? So if you want to think about it, moving it as a chunk, I would be subtracting the whole chunk, 2 plus the square root of 7, from both sides. So that's going to give us x minus the 2 plus the square root of 7 as one factor, because again, it's going to be set equal to 0. Then our second factor, I'm going to change colors so you can see which one's associated with which. So I'm going to go to purple for this one. Purple. Where's purple? Where's purple? All right. Then for this one, again, think of it as a chunk. We're going to subtract the 2 minus root 7 all together from both sides. Subtract 2 minus 7. So that's going to give us the factor x minus 2 minus root 7. So there's our second factor. And then our third one, and again, I'm going to change them so you can see. Let's go dark blue. Nope, let's dark. Okay. So then we would subtract 3. And our last one would be x minus 3. Okay. So again, list each individually. So once you're there, like I'm okay with this. I don't recall having to do the weird zeros. Technically, you could distribute that negative so that we wound up with x minus 2 minus square root of 7 as one factor. It just looks a little weird. And then distribute this next one, x minus 2 plus the square root of 7 as another factor. And then the x minus 3 is just x minus 3. So either one of these should be fine for your, let me get this out of the way for your try me. Should be fine for your answer. I'm trying to box this in. For your product of linear factors. So yeah, because we had complicated roots, we have a very strange looking linear factor grouping. All right. The rest are you try it, so I will leave you to that and you can check them with the completed key. I'm going to adjust this because when I upload it as a PDF, it will chop all of that off. So let me bring this all the way up here. We'll do a little separation so we know those are the possibles. And then let me drag all of this up here. That way, if you need the completed notes, it shouldn't chop anything off.